Okay, so remember what we're talking about, right? Talking about continuity, and we gave two definitions. Can somebody give one of them?
I'm looking at it, so do you?
All right, go ahead. F is continuous at some point, x naught if something happens, right? So there's two definitions, one involving sequences, the other involving epsilons and deltas, or neighborhoods, epsilon neighborhoods and delta neighborhoods, right? Given any sequence, if given any sequence x of n such that x of n converges to x naught, f of x n converges to f of x naught. Right? That was definition number one. Definition number two. Somebody tell it to me. Epsilon delta. Given any epsilon, there exists a delta such that, okay.
That the difference in f of x is less than epsilon, and you can map that to difference less than delta?
Not exactly. But good for trying. So here is f of x naught, and here is x naught. Okay. It says that, so yeah, it's a good thing, right? You try an answer and get it corrected, and try an answer and get it corrected, right? The quickest path to learn is to make mistakes. I encourage you all to be more shameless, right? This is the advice that my Chinese teacher gave us when I was learning Chinese in college. He said, the key to learning is shamelessness. And it's true. So yeah, we're good. So it's rather like this. Here's the picture. Part one, given any epsilon neighborhood here. Part two, there exists a delta neighborhood here, such that blah blah blah, such that the guys here get mapped inside there. Okay. So, given any epsilon, there exists a delta. So there's an order to this, right? Given any epsilon, there exists a delta, such that any x within delta of x naught satisfies f of x minus f of x naught is less than epsilon. Okay. Anybody in the delta neighborhood, its image lies in the epsilon neighborhood. Okay. Okay. So, okay, let's give the proof of that. I'm sorry, let's give the proof that those two things are the same. Okay. So, so I'm going to call this our definition. Okay, this is what we're going to use as the definition. This we're going to show is equivalent to the definition, but this is not our definition. Okay, so if I ask for a definition, I want you to say this. Okay, this is what we're going to treat as our definition, even though they are equivalent. Let me remark that in topology, if you ever take a course in points of topology, you'll be dealing with different spaces. Okay, in any metrizable space, these are equivalent. Okay.
What is
these?
metrizable?
It means that you can put a metric on it.
Ah.
Okay. You guys are doing metric spaces. It means, say, if you have a space with a metric, then these definitions are equivalent.
You never actually defined metric space.
We haven't yet, but we will learn about it at the end of the course, thanks to the group 2 or 1, whichever one you want to call yourself. 1. Okay. So, so theorem, f is continuous at x. The second definition is equivalent to the first definition, right? It's equivalent to given any sequence converging to x, f of xn converges to f of x naught. Sorry, x naught. This is x naught. Okay, so let's show that if you have the epsilon-delta property, then any sequence that converges to x naught is going to have its image converge to f of x naught. Okay.
It's definition.
Hmm?
Isn't that just like its definition?
No, the definition is the epsilon-delta thing. Okay, we assume that we have the epsilon-delta property, right? So, yeah.
Just wondering, so for the homework, for the second group problem, do you want us to show it both ways?
The second group problem.
Yeah, the second group problem is the two definitions of subseed, of lim suit.
Yes, it has to go both ways.
Okay.
Yeah, absolutely. Okay. Okay. So let's do it. Let x of n be some sequence converging to x naught. Okay. We want to show that f of xn converges to f of x naught. Okay. F of xn converges to f of x naught. What does that mean? Given any epsilon, what does it mean for a sequence to converge? Given any epsilon, there exists an n, right? There exists an n such that if n exceeds m exceeds n, then f of xn minus f of x naught is smaller than epsilon. Okay. So if we have an x naught, we have an f of x naught, and somebody says, I'd like you to find a time past which everybody is within this epsilon neighborhood of f of x naught, right? You have your first sequence, you have your sequence converging to x naught, right? And they say, I'd like you to find a time past which everybody in your sequence, I'd like you to find a time past which everybody in your sequence lies in this epsilon neighborhood, right? You see how, does anybody see how it's going to work? You already know that there's a delta neighborhood such that everybody gets mapped into the epsilon neighborhood, right? So what do? Just choose the time past which everybody's in the delta neighborhood, right? Which you can do because these guys converge to x naught, right? So it's easy, right? You say, well, look, since f is continuous at x naught, there exists a delta neighborhood such that if the distance of x to x naught is smaller than delta, the distance of f of x to f of x naught is smaller than epsilon. Right? But you also know that the xn converge to x naught. Right? So there exists a time past which all the xn's are in that delta neighborhood. Right? The xn converge to x naught, right? We have a magic delta neighborhood in which everybody satisfies, everybody's in here. And we know that these guys converge to x naught, so there's some time past which everybody's in the delta neighborhood. So there's a time past which all the outputs are here, right? and thus f of xn minus f of x naught is less than epsilon. Okay, so we found the n that we're looking for. We wanted an n past which all the outputs were within epsilon of f of x naught, and we found it. Okay. So you see that the epsilon delta definition implies the sequence definition. Okay. Any questions? Any questions? Don't worry if you don't understand it. Worry if you go home and you still don't understand it. Okay, so don't, I think I've said this before, I often do not understand a word of what my professors said in class, but I went home and thought about it a lot. And then I understood it, right? Or I got some understanding, some lousy understanding of it. Yes, Mitchell?
So the continuity definition says that the limit as n approaches infinity of x of n is equal to x naught?
No. So, are you talking about the epsilon delta definition or the sequence definition?
I think I'm talking about the sequence definition.
So the sequence definition is that
Okay.
given any sequence converging to x naught, the image of that sequence converges to f of x naught.
Okay.
Okay, so no matter what sequence I choose here, the images will converge to f of x naught.
Okay.
Okay, don't worry. Go home and think. Okay, now let's go backwards. Suppose we satisfy the sequence definition, right? And we want to show that we satisfy the epsilon delta definition. This is a little bit trickier. Okay, so right. So you want to show the epsilon delta definition, right? That given any epsilon greater than 0, there exists a delta greater than 0 such that f of that delta neighborhood of x naught is contained in the epsilon neighborhood of f of x naught. Okay, so I'm writing it in the neighborhood notation. So we have x naught, we have x naught, we have f of x naught, right? Somebody gives you an epsilon neighborhood, and you want to find the delta neighborhood. You want to find the delta neighborhood that gets mapped inside there. Okay, I'm going to do this by contradiction. Suppose there is a bad epsilon. Okay, there's an epsilon that we cannot deal with. Okay, right. Yeah. Okay. What does that mean? That would mean that there is no delta that works, right? There's no delta such that f of this thing is contained in the epsilon naught neighborhood. Okay. Well, think of what that means in the picture. Right? Here is f of x naught, and here is the bad epsilon. Okay. You want to throw it out of class, this epsilon. That's how you feel about it. Just okay. So what does it say? That no matter what delta you choose, there's somebody inside here that doesn't go into the epsilon neighborhood. Right? So no matter what delta you choose, there's somebody outside. Right? It doesn't get mapped inside there. Right? So let delta n be 1 over n. Okay, so we're going to take a sequence of deltas. They all fail, right? Then there is a is an exaben in the delta neighborhood of x naught, such that f of xn is not in the epsilon neighborhood. Right? In other words, the distance of f of xn minus f of x naught exceeds epsilon. Okay? How does that give us our contradiction? We've created a sequence, exaben. The exabens are within, each exaben is within 1/n of x naught. But the f of exabens all lie outside the epsilon neighborhood. So?
Just choose a different epsilon.
No. No. What are we trying to contradict? We're trying to contradict our assumption that we satisfy the sequence definition, right? So assume f satisfies the sequence definition, right? In other words, if xn goes to x naught, then f of xn goes to f of x naught. Right? But you see what happens? We've just constructed a sequence that converges to x naught, but its image does not converge to f of x naught. Contradiction. Right? Then xn converges to x naught, right? Because the distance is 1/n, right? So these guys get closer and closer to x naught, but f of xn does not converge to f of x naught. Contradiction. Okay, any questions? Okay, so the definitions are equivalent. Okay, let me show you an example of how one proves continuity for a slightly more complicated case. Okay, so slightly complicated example. So f of x, say, is 2x squared plus 1. Let's show that f is continuous on the reals. Okay. So one way is easy. Okay, let's use the limit, the sequence definition. Okay, so suppose xn converges to x naught. Okay, we want to show that f of xn converges to f of x naught. In other words, that the limit as n goes to infinity of 2n squared plus 1 equals to x naught squared plus 1. Okay, well, why is that true? That's definitely true, because of our
Definition.
what? No, not a definition. You have some theorem about this, right? You have a sequence that converges to x naught. So the limit of this thing, the sequence squared plus 1. What's the theorem? Limits in arithmetic, right? So by limits in arithmetic, done. Right? Right? True by limits in arithmetic. So you could, if you wanted to use a sequence definition, that's how you would do it. You can see by the fact that I'm erasing more of the board that the other way is going to be more complicated. Okay, so let's do that the second way over here. Okay, so using the epsilon-delta definition. Okay, not to say that this is worse, but I actually like this way better. I think it gives you more of a hands-on understanding of how to do it. But anyway, okay, so fix epsilon greater than 0. We want to show that there exists a delta greater than 0 such that if the distance of x from x naught is less than delta, then the distance of f of x from f of x naught is less than epsilon. Okay. So here's the scratch work. Right? We're gonna have to get our hands a little dirty. Okay. You say, okay, well, let's look at this thing. F of x minus f of x naught is x squared plus 1 minus x naught squared plus 1 in absolute value. I'm sorry, 2x squared, 2x x naught squared. Right, of course. Right? The ones cancel off, right? And you end up with 2x squared minus x naught squared.
Plus x or plus 1?
Sorry. The ones get canceled off.
Oh, yeah.
It looked like X.
Sorry, looks like an x. The ones get canceled off. There you go. You can pull the 2 out, you get 2x squared, 2x minus x naught, x plus x naught. Okay, so we want a delta. Think what we want, right? We want a delta. We want delta such that if x minus x naught is less than delta, then this thing is less than epsilon. Right? We want a delta such that if this is less than delta, then this thing is less than epsilon. Right? Okay. Now let me say something wrong. So take delta to be smaller than epsilon over 2x plus x naught. Right? Then, right, if this thing is smaller than epsilon over 2x plus x naught, then this product is going to be smaller than epsilon. It's true, but wrong thinking. Do everybody see that it's true?
Yeah.
Okay. Right. If this thing is smaller than epsilon over 2x plus x naught, then this product is smaller than epsilon. Okay, but we can't do that because the x is changing. Right? The x is changing, so this, what does it mean about the delta?
It's changing.
The delta is, we don't know what it means. We don't know what the delta is, right? So there is no fixed. We don't have a fixed delta. We need a fixed delta. We don't have a fixed delta. Okay. But you play a trick, and the trick is you say we will consider only delta less than 1. Okay. We restrict ourselves, right? We restrict ourselves to delta less than 1 and greater than 0, of course. Okay? Like we say, I swear I'm not going to use any I'm not going to use any delta bigger than 1. Okay? That's okay because it just makes things harder for us, right? Right? We assume, like, right? Initially, we were allowed to choose any delta, right? So we say we're going to only look at the delta between 0 and 1. Okay? But in that case, you see that x plus x naught is less than or equal to, so if the distance of x from x naught is less than delta, so here's my x naught plus 1, x naught minus 1. Right? We see that you see that x plus x naught is smaller than x, absolute value of x plus the absolute value of x naught by the triangle inequality. Right? But you see that the absolute value of x is smaller than absolute value of x naught plus 1.
Because you would have broken up the line above into triangle inequality too?
Well, think, here's your x naught, right? And you know that the distance of x to x naught is less than 1, right? So the size of x, well, that's the same thing as the size of x minus x naught plus x naught. And you use the triangle inequality, that's less than or equal to this, right? But this is less than or equal to 1. Okay. So the size of x is controlled by the magnitude of x naught plus 1. Okay. So,
X naught plus 1 plus x naught?
yep, right. In other words, 2 x naught plus 1. 2 magnitudes of x naught plus 1. Okay. So, here's what we can do. We take delta to be smaller than this. Right? We take delta to be smaller than this. Right? And that will make the product less than epsilon.
2 times 2 times.
That's right. Yeah. Right. We can't use that x plus x naught, but we can use this. Okay. Sorry, I'm just going to take. I'm sorry to keep you over, but let me just write up the argument. So, given epsilon, let delta be the minimum of 1 and epsilon over 2 times 2 x naught magnitude plus 1. Okay. And we throw in this minimum 1 to reassure ourselves that our delta is smaller than 1. Okay, right, this is, I'm sorry, maybe I should say less than or equal to 1. It doesn't matter. Okay. Then if x minus x naught is less than delta, we see that f of x minus f of x naught, which equals this, is less than or equal to 2 epsilon over 2 x naught plus 1 times x plus x naught times 2 x naught plus 1, right, which is epsilon. And maybe I should have made this a little bit smaller because it looks like I'm getting less than or equal to epsilon. So maybe I divide by 3 here instead, and it'll be less than epsilon. Okay. Doesn't make, and if you want, I can divide by 10 to the 10th or something. Okay, I'm sorry to keep you over, but that's the end.